So I'll get you guys to start off with just a little connection to what we've done last lesson. I'll have you think about these different types of forces that are described on the left-hand side: weight force, air resistance, the applied force and applied force, normal reaction force or friction. And on the right, I have their definitions, but they're all jumbled up. So see if you can make a connection between the force and its correct definition, and just note down maybe you can paraphrase some of the keywords in the definition. You don't have to write the whole lot down, but make a connection between what is the force name and its meaning. Okay. So what do we have? Weight force. What is the definition or meaning of a weight force? Mitchell? Yes, acting on a mass. What does it depend on, the weight force? Absolutely. So that aligns with that definition right there, yeah? So weight force here, force acting on mass due to gravity, directly vertically downwards. Okay. Air resistance force, how would we describe that? Which one does that apply to? Yeah, last one, a force exerted on an object by moving through atmosphere. What makes up the atmosphere? Air. What makes up air? Particles, objects, little masses themselves. And they're constantly colliding with an object that has a surface that is trying to pass through it. Alright, what about friction? Second one? Second last one. Okay, reaction force exerted on an object from a rough surface. Very good. So, being a rough surface, it's not perfectly smooth, even though we look at a table and go, oh yeah, it's pretty smooth. But at the microscopic level, it's actually, quite rough. It's hilly almost from the perspective of an atom. You've got the Grand Canyon in there. So, and the same with skin. And skin is very rough, and you can experience friction by rubbing your hands, because this creates that friction force. Friction force does work on your hands, on the layers of skin, which generates heat. Okay? Alright, and applied force. If we're talking about applying a force to an object, what can we describe that as? Absolutely. Simply a push or a pull on a mass. Okay, that creates an unbalanced force. And then a normal reaction force. Well, this is one where when you exert that onto an object like that has a surface, then that surface reacts and applies a reaction force back onto the object as described in Newton's third law. Alright, so based on that now, we're going to examine different scenarios where we've got a number of these forces involved. Okay? So, today's focus, we're going to be looking at, we want to be able to examine motion due to forces. Okay? And the way we do that is by a relationship as described by Newton's second law. Who remembers Newton's second law? Sinay, that's yours, mate. Go for it.
Second law.
Yep. That's no. Third law is for every action there's an equal and opposite reaction. So one down. Nephew, you had your hand up first. Say again. Okay. Second law states that force as a quantity is equivalent to the mass of the object multiplied by the acceleration. Yep. F equals ma. So it's the acceleration part that determines the property of motion for an object. And if we know the overall force, then we can relate that to the object's acceleration. So when we talk about force equals mass times acceleration, specifically there's an important type of force, okay, that is directly related to the object's acceleration, not just force in general. Come here. What is it? The net force. Yes, very good. So the net force, or the overall force, when you look at all the forces together and you think about, well, if we combine all those forces, what's the overall force we get, then that will be directly related to the object's acceleration, depending on how much mass it has. Okay? And that's our goal. So we want to be able to determine the net force, and we want to be able to then figure out, well, what's going to be the resultant acceleration of the object once we know the net force. And we're going to look at some specific examples. One example today is thinking about this quantity called terminal velocity of an object that experiences a force due to gravity and air resistance. What do you think terminal velocity means? What does that relate to? Zach. Very good. The highest point that the velocity reaches, or the largest possible velocity. Okay? Which is a good thing, because you don't want to keep accelerating towards the ground if you're falling and get faster and faster and faster. By the time you hit the ground, probably going too fast to be able to stop. The ground will stop you, but it'll be, a bit of a mess. Alright, so what we started looking at last lesson is the idea of, how we can go about drawing and showing all the forces acting on an object. So I'm going to get you to do this as a drawing exercise. So here's the three objects, the three diagrams. Pass one along. One more, please. Okay, so to help us to identify all the forces acting on these objects, I want you to consider, as you think about the forces and the definitions that we've just written down, I also want you to keep in mind Newton's third law. Every applied force, there's a equal and opposite in size reaction force. So the fundamental idea from last session was that these forces all exist in pairs. Okay? And what I want you to do is, as you draw a force acting on an object, I want you to follow a certain format in the way you draw and label the force. So on the page that I've given you, I want you to represent the force using an arrow, a directed line segment. Now try and show the two important quantities or properties of this arrow. That is, the size of the arrow matters, and then the direction of the arrow matters. Okay? But then I want you to label the force. So you might use a capital to represent the force, and then we want to write some subscripts to say that what was the object that caused the force and what was the object that received the force. So you might say this is a force from object A onto object B. From A onto B. Alright, so the mass, the object experiencing the force is the second one, the B. From A onto B. So the first example might be, alright, here's the man pushing on the crate. He's applying an applied force, a push force. So he has one force, and this is a force from the man onto the crate. And Newton's third law said that for every action there's an equal and opposite reaction. So that might mean from there we have another force, a reaction force. And what label can we use for this reaction force? From the crate onto the man. Very good. This is a reaction force that the crate exerts back onto the man. Does everybody understand? So I'll give you a few minutes, see if you can look at the diagram and think about all the situations, all the possible situations where a force might act on an object. That could be on the man as well as on the crate, for instance. And see if you can label all the different types of forces. Okay. Thank you. Let's quickly review. So for the first one, ladies and gents, we examined so far this push force that the man exerts on the crate. Crate reacts and exerts back onto the man. Now, there is a second pushing force in this scenario. Where would that occur? Think about point of contact. Crate to the ground, very good. So we've got a push here of the ground is pushing back onto the crate. So from the ground onto the crate, and then equal and opposite reaction where the crate pushes onto the ground. Which one's likely to move?
What do you mean if friction is smaller than the
That way, yes. Is there a fight between these two forces?
Oh, it's just like that.
Equal and opposite, balancing each other out? You might say, well, neither of them, if the crate is just sitting there and the man's not pushing it, is the crate likely to move because of those two forces there? No. So there has to be a balancing. What's causing a balance?
The opposite direction.
Is there another force? Very good. Force due to gravity, force interacting with the earth. Now that's different than the force of the object acting with the ground. Alright, it's very different. So, due to the mass of the crate, we have a force that the earth pulls onto the crate. So the earth pulls down. Gravity, you got to think of gravity or the weight force as a pulling force, and that is the earth pulls onto or acts the force onto the crate, pulling it downwards. And then equal and opposite, there's the same weight force, but this now is where the crate pulls back onto the earth. Okay? Because the earth is so massive, it won't accelerate. Okay? Alright, any other forces? What was another that was observed? Force due to friction. Yes, absolutely. So Which way do you think the force due to friction is acting on the crate? Which way? That way? Opposite direction? So we've got one force due to friction that this is a force that the ground, the surface of the ground is acting on the crate and opposing its motion, pulling it backwards that way. But Newton's third law says there's an equal and opposite reaction force that the crate is pulling onto the surface of the ground. But because the ground is so solid and so massive, the ground's not going to be accelerating or sliding in any such direction horizontally. Now, there's also another fundamental force which helps to explain exactly what causes this push. Now, the man is able to push the crate, but is he still able, I want you to think about this question, is he still able to exert this pushing force on the crate if he was standing on perhaps like a block of ice or a slippery surface? No, he wouldn't be able to do it. So what enables him to create or generate such a pushing force? Friction. That's right, what a friction. Friction between what? His feet and the ground, absolutely. And if it wasn't for the friction between his feet and the ground, he won't be able to push the crate at all. So, from here, as he pushes his feet against the ground, all right, which way is he pushing his feet or wanting to move his feet to be able to push the crate? Opposite direction. So if we put our hands up against the bed and we're pushing this way, our back leg, our muscles are applying and exerting force in the opposite direction for which we're trying to push. So we've used our leg muscles to push this way, and our hands are pushing that way because that's the mechanics of it, and we're taking advantage of the friction of the ground. So the pushing force due to friction of the foot is this direction. Okay, this is from the ground onto his shoe. And then equal and opposite, going the other way, of the shoe back onto the ground. Now, I made a mistake. Who can help me? Think about these two here. Force of the ground onto the shoe, and the other one, the force of the shoe onto the ground. Is that correct? No. Which one is the action foot? Which one is the action force? It's going the other way. The action force is him applying the action of his foot pushing back on the ground in the opposite way. And then the floor reacts and pushes back on him in the direction that he wants to move. So we're going to stop those two. So if you like to try and rewrite these and draw these again, I'll get you to set it up nicely again, perhaps in your exercise book. Now, so these are the forces acting on the man, and where they act on the man, the applied force will be the larger force, and then that acts onto the crate. So now this is where you think about all the forces acting on the crate. If we wanted to examine the motion of the crate, then every force that has a subscript C that comes second, that means these are the forces that are acting onto that object, the crate. So all the ones that are where the C are second, those are the forces acting on that crate specifically. 1, 2, 3, 4. So there are 4 overall forces acting just on the crate. So it is then the net force, overall force of all those 4 forces that causes the crate to accelerate. Which way is it likely to accelerate? Which direction? To the right. So we're expecting the crate to begin accelerating with some amount A towards the right. Which direction do you think the net force should be in? Should be the same, Buddha. Yeah, absolutely. So the net force is the same in direction because net force is a vector, acceleration is a vector. So the direction of the acceleration is the same as the direction of the net force. What relates acceleration to net force all depends on a scalar quantity, which is just the size only, which is the mass of the crate. Okay, so your net force overall must be toward the right, but there are forces going up and down. See all the blue forces acting on the crate going up and down? Why isn't there an acceleration up or down? What's happening to those forces? They cancel out. Very good. They balance. They balance each other out. So if they're balancing each other out for the forces going up and down, what should be the size of the net force? 0. Very good. So vertically, if you look at all the vertical forces, yeah, we're getting a overall net force that is equal to 0. So there's 2 forces that are traveling vertically that result in a net force of 0. We've got this force here, force that the Earth pulls onto the crate, that's the weight force due to gravity, okay, going down, and then there's this other force here that the ground pushes onto the crate. So out of those 2 forces, how should they combine? What operation should we have between them to be able to make the net force? What should they do to each other, those 2 forces? Cancel out. How? Equal and opposite, so one of them must be negative, a subtraction. Absolutely. Because they're actually this supporting reaction force that the ground exerts back onto the crate, okay, it's equal and opposite to the weight force pushing back down onto Earth. But it's not, the ground force is not the equal and opposite pair of the force due to gravity, okay? Because those 2 are the pairs, whereas those 2 are the pairs. Does that make sense? But there's still 2 different forces that acting in opposite directions but equal in size, and they cancel each other out, they balance. Okay? Very good. So, now, we'll just examine one more. This second one here. I'm not gonna cover it in same detail, but this time we're just going to identify only the forces acting on the crate only. All right. So one from the center of the mass of the crate, what could I show? Miguel, what could be one obvious one?
Gravity.
Force due to gravity, good, straight down towards the ground. So the one due to gravity that interacts with the earth pulls down towards the ground. What's the name of that force? That from the definitions we did at the start. Weight force. So this is the weight force acting on the crate, pulling it down towards the ground. Now, this is on a surface. And what's the surface doing to the crate? It's causing friction, absolutely. So, if the man is trying to push it up the hill on this incline, which way is friction going? Pulling it down. Alright, so here is a force due to friction, pulling it back down. This is a friction acting on the crate. Is there any other forces acting on the crate? Plane force, yes. This is called the normal force, where the contact between the surface is pushing on the crate. Which way is that going? Perpendicular to the surface, very good. So it comes up this way, comes out exactly 90 degrees. It's called a normal force. Normal means a 90-degree angle out from the surface. And it's actually pushing it out this way. This is the normal force. All right, very good. Are there any other forces acting on the crate? It could be if he's in motion and he's moving really fast, because air resistance depends on velocity. So John Ray, if he's moving slow, do you think air resistance is going to be significant? No, but it's good to point that out. Yeah? But there's an applied force. An applied force from here of the man pushing. We'll use P for a pushing force or an applied force.
So, contact.
Because it's contact, yeah. And what we have, and what makes this even a more fun exercise, is the inclined plane. It all depends on the angle of inclination, yeah? Now, which way do you think the crate is likely to accelerate? If he's pushing strong enough? Yep, it does. Pushing up that way, which is parallel to the plane. So if he's pushing hard enough, that means his P force is larger and overcomes other forces, then it will push up the plane. Which force out of the push force or the normal force or the weight force or the friction force, which ones do you think might depend on the size of the angle of the incline? Friction, good. So friction. What else? The applied force depends on the angle.
It's harder to push it.
Yes, why is it hard to push it?
This is what it is.
Yep.
Really dragging it back.
Yes. So, but what's important to see is that the push force here is always going to be exact same direction as acceleration if he is able to push hard enough. So the direction of the push force won't change. The push force will be the same as the acceleration. But the magnitude, absolutely, the size of the push force definitely does depend on the angle. So let's focus just on the direction for now. So the friction. What about if we rotate the plane upwards? Which ones are going to move differently? Normal force, yes, normal force will rotate out this way. Yeah, that force will rotate. Is weight force going to rotate? No, rate force is always directed downwards. Yeah? So friction, normal force will change. And so on. They depend on angle. All right. So what we're going to examine more specifically now is another case of a different type of force where we look at air resistance. So we've examined the force due to air resistance last semester. Just a little technical, this is on the other side of the exam. So when we have an object, this is another situation showing the forces acting on the object. This one's falling towards the ground. It falls because it's experiencing a weight force. So an important formula to help you to calculate the size of a weight force is you need the mass of the object and then you multiply by your G constant. What's the size of that as a number? Very good, 9.81. And it's an acceleration actually, so it's meters per second squared in units. Now, force due to air resistance pushing back up. So this object's going to keep traveling faster and faster towards the ground. And as you go faster and faster towards the ground, what would happen to the size of the force due to air resistance? What should happen to it? It should increase. It should get bigger and bigger and bigger. How big can the force due to air resistance get? Only equal to the weight force. Well done, Miguel. Gentlemen, hypothetically, if the force due to air resistance gets larger than the weight force, what would happen to the ball? It would go upwards, back into the sky. Yeah? Which doesn't happen. So, in other words, force due to air resistance can never be larger than the weight force. Okay, so let's look at the net force. Now, when we add up all those two forces, we've got our force due to air resistance heading in one direction, okay, and then we've got plus the weight force. Now, to be able to show that properly, what do I have to remember to do with these two forces when I'm trying to work out the net force? Subtract, very good, because they are going in opposite directions. So you've got to remember to show that one of them is going to be subtracted from the other. All right, now if this is moving downwards and with that acceleration towards the ground, okay, that's in the same direction as the weight force. Yes? So if I want my acceleration to be positive, that means this right-hand side quantity needs to be a positive amount. That also means my left-hand side quantity, my net force, must also be a positive amount. So if I want the net force overall to have a positive number, which of these two forces will stay positive and which one will I make negative? Very good, the weight force will stay positive, and so then the force due to air resistance has to be subtraction, has to be a negative quantity. Okay? Now, which one's going to be bigger overall? Weight force, very good, because this has to stay positive. Okay, so from this now, we said that force due to air resistance can never be larger than the weight force. Can never be larger. So that means it's either going to be smaller or equal to. Yeah? Now, if it goes equal to, what happens to the net force? Becomes 0.
Oh my god.
That's not that revelating, gentlemen. All right. So the net force can go to 0. And when you get this scenario, that means you've got 0 net force. And if that's a 0 net force, what can we conclude about the acceleration of the object? Yes. So object is not accelerating now. So if the object's not accelerating, that means it's not speeding up. Yeah? What is it doing then if it's not speeding up anymore? Traveling at a constant speed. Yeah? Object is not accelerating. Well, your parents do it all the time when they're driving on the road to stay at the speed limit. Yeah? They travel at 100 kilometers per hour and they don't accelerate anymore and they travel just at a constant speed.
One more question.
Yeah.
It was like 18 to 65 grams. I'm surprised. Like up from shout out to the same
Okay, so let's consider what that looks like. So this is a velocity versus time graph. We'll finish off with this one. Now, this velocity versus time graph has two versions. One that has air resistance when it's falling, one that does not experience air resistance in a vacuum perhaps when it's falling. Which one do you think is an object falling in a vacuum?
Oh, no.
That's right. So this is no air resistance, which means it just continues to accelerate and get faster and faster. Okay? This one has air resistance. And you can see it slows down in velocity. It slows down. It's not slowing down, but the acceleration is coming down to closer to 0. But you reach a maximum velocity, which is called a terminal velocity. So,
Or would it be like, would it stay at the exact point, or would it be like an asymptote?
it will be asymptote. Very good. Well done. Zach?
Technically, is it the terminal velocity? It's just gets closer to 1 velocity.
Yes. It's the theoretical maximum velocity. Well done. Now, just to build on that, now, we know half-pack rule. Now, when they're equal to each other, when they subtract and they equal to 0, the two forces balance. And a balancing two forces means that the weight force given by mass times gravity is the same as the force due to air resistance given by half-pack. Yes? And when you equate those two formula, you see, you've got an expression to solve for velocity. And that velocity is a special formula to work out what's called the terminal velocity of an object. Okay, so I'll put that up as on our very next lesson so you can add it to your notes. And then we're going to do some problems around terminal velocity. Okay?
It only applies when it's in vacuum.